Hello, and welcome back to my physics online video lecture series. Today's video, we're going to be talking a little bit about thin lenses, specifically some of the equations that you might want to use with thin lenses, not to be confused, of course, with Thin Lizzy. The thin lens equations that we're going to be looking at basically are for essentially using these lenses to find images of objects. There will be a separate video to go over ray diagrams associated with thin lenses. So let's first look at a few things, define a few things, etc. Some major things that we need to define, the main variables are DO, DI, and F. Okay, so DO will represent object distance. Essentially what this is the distance between the object that you're using the lens to image and the lens itself. DI we're going to use to represent image distance. So this is, again, the distance between the image being formed by the lens and the lens. And F is what's called the focal length of the lens. So the focal length is sort of best defined as if you send a bunch of parallel rays through the lens, where do they come to a focus, and how far really is that from the lens? By analogy, if you were to take a lens outside into bright sunlight, you can hold it up over a leaf or some paper and basically burn the leaf, burn the paper, that kind of thing. So how far is it from where the lens is to where you have to hold your leaf or your paper or whatever to get the most concentrated sunlight? That distance is your focal length. And actually, for all these distances, distance is loosely taken from center of lens. Now with a thin lens, we basically treat it as if it has a thickness of 0, and so the lens just is at the center of the lens. By sort of schematic, if this is representing my lens, this little dashed line that I've drawn is the center of my lens. And so if I have, let's say, an object here, so we'll call this my object, then this distance right here would be DO. If I form an image somewhere over here, then this distance would be DI. And if my focal points are, maybe like here and here, so essentially this would be my F. Okay, so those are some of the things that we need to define. The other pieces that we got to define to make this work is lateral magnification. So the magnification, or lateral magnification, M, actually is defined by the height of the image divided by the height of the object. So what are these HO and HIs? If this right here, again, is my object, then this distance from this axis running through the actual literal center of the lens to the top of the object could be my height of my object. And then this distance right here would be my height of my image. So this right here is how those two are defined. As it turns out, this lateral magnification is equal to the negative of DI divided by DO. So these are two of your equations. Two more equations that you may need are what are called the lens maker's equation and the thin lens equation. So let's look at those two. The lens maker's equation is basically for essentially if you have a thin lens, it kind of like this is how you determine what the focal length of that lens will be. And it's actually defined in terms of two faces. All right. So the actual equation for the lens maker's equation basically is defined in terms of the refractive index of the lens itself. So this is lens material, and of the surrounding media. So typically this is air, but it could be water or vacuum or whatever. And these are refractive indices. And then R1 and R2 represent the curvature of the two faces of the lens. So if I were to look at the lens, maybe I have a lens that happens to be shaped something like this. So I have one face here, I have one face here. The radius basically is, if I were to continue this face off to make a complete sphere, as it turns out, then what would the radius of that sphere be? So here's the center of the sphere for face number 1. This would be R1. Let's say maybe over here somewhere is the radius for sphere number 2. This would be R2. So it's basically radii of curvature. If you have a flat radius, then it's infinite. Incidentally, if the radius is like this, kind of bulging towards you, we're kind of assuming that you're looking this way through it or you're imaging this way through it. If it bulges outward like this, then this one counts as convex and has a positive. This one also is convex, but in this case it's bulging away from the source, so it actually counts as a negative. So 1 over R1 minus 1 over R2, you're actually adding, you're taking a positive number and subtracting a negative number, which is like adding two positive numbers in this equation. In 1 and in 2 are your refractive indices. So kind of conceptual example of this lens maker's equation. Let's just copy it over to the next slide here. Conceptual example of this guy would be that, let's say I have a lens made of glass, and so that is refractive index, let's say 1.5, placed in air. Then that would be equivalent to refractive index 1 being approximately 1.00. Okay, and so essentially this number would be 1, so you'd have 1 over the focal length is equal to 1.5 minus 1 times your 2 radii. So maybe it is R1 equals R2 equals, let's say, like 25 centimeters of curvature. And it's what we call biconvex. So biconvex basically just looks like this blue lens that I've drawn here. So you'd have 1 over 25 centimeters here minus 1 over negative 25 centimeters, because one of them is bowing towards you and the other one over here is blowing out but away from you. Okay, and so you'd end up with 1 over F is 0.5 over basically 2 times 1 over 25. And so you'd end up with 0.5 times 2 over 25 centimeters, which just is 1 over 25 centimeters. And so your focal length f in this case is 25 centimeters. All right, so that's the Lensmaker's equation. Basically, it's called Lensmaker's equation because it's, in some sense, literally the equation that a person trying to make a thin lens would use if they want to, let's say they need to make a lens that has a focal length of 50 centimeters. They know what the material is going to be. They know that it's going to be used in air. It's telling them essentially, like, how do I need to grind these two surfaces of the lens, this surface here and this surface here, so that I get that focal length. And usually, though not always, these two either have the same radii, or you'll get some that are like this, where one face is flat and the other face is part of a sphere, essentially. So if it's flat, then the radius is effectively infinite, and so 1 over r is 0. And so we only would look at the front face in that case. Okay, the other important equation for thin lenses is what's sometimes just called the thin lens equation. And what that does is we come back over here where I've defined DO, DI, and F. That equation relates the three to each other. It basically just says 1 over DO plus 1 over DI is equal to 1 over F. And again, I'm not going to derive this equation for you. You can derive it geometrically if you've made appropriate assumptions about thin lens and so on. That would take a bit long for a short video. This is the actual equation in action. So now let's do a quick example with it. All right, so how far from a lens of focal length 25 centimeters will the image be formed of an object 75 centimeters from the lens? Sometimes it's nice to draw a brief sketch, even if we're not drawing really a ray diagram, just to see what's going on. Essentially, you have a focal length here and here. Your object is placed somewhere over here. I'm going to label this object. Your image you expect to be formed somewhere. You're just doing the math to figure out where. So 1 over DO plus 1 over DI is 1 over F can always be rewritten as 1 over DI is equal to 1 over F minus 1 over DO. And so making use of that, I have 1 over DI is equal to 1 over 25 centimeters minus 1 over 75 centimeters. Now, 75 is 3 times 25, so this is the same as 3 over 75 minus 1 over 75. And so 1 over DI is 2 over 75, and that means that our image is being formed DI 75 over 2, or if you prefer, 37.5 centimeters away. So our DI ends up somewhere like maybe right here, essentially. So here's 25, here's half again that distance, which is 37.5. Follow-up to that example would be to ask about the magnification and orientation. Okay, the magnification M, again, can be given by negative DI over DO. So we just found that that was 75 centimeters divided by 2 for the image distance. The object was 75 centimeters. So I have half of something divided by the something. That means that I have a half. There's a minus sign out front, so this is minus a half. So the magnification is minus a half. That means that the orientation will be inverted. And not only is the image inverted, or in other words, upside down compared to the object, but its height is half as much as the height of the object. And that is sort of the key equations for the thin lens. So thanks for watching.